Hello, in this lesson, we're going to talk about the definition of a limit at infinity. Okay, we see these wording often. This is how we read the limit. You will read the limit as the limit of f of x at infinity. That's how you read it. And previously we had notation on limit, right? The intuitive definition of limit, which is right here. It says the limit of f of x as x approaching a. Oh, I'm missing an x here. Oh, wait a second. I'm missing x there. There. Okay. As x approaching a, this can also be read the limit of f of x at a. So this is, typical reading. So that's how you read it. But the best way is still to just write it down. Write it down concisely, so there'll be no confusion. Okay. And we have studied the functions, limit at a finite number. A is finite number, and we studied, if the limit does not exist, which one of the form is the limit is infinity, positive infinity, or negative infinity. And this time we have learned all of these properties about limits, right? We emphasize the importance before we can use these limit properties, limit laws, which is that the individual limit must exist. We need to verify that these limits exist before we can apply the laws of limits, where we have so many of them, right? We have also studied the continuous function. So at this moment, we're going to study the limits at infinity. What does it mean, limit at infinity? It just means that when the input x is approaching infinity, it could be approaching positive infinity. It could also be approaching negative infinity, right? So in this case, you can see that there are different ways x may be x approaching infinity, right? So I'm going to draw a picture. So you see x is approaching infinity, right? X is getting as large as possible, right? It's a dynamic process. As x is getting larger and larger, the y value, f of x, which is a vertical, right? Which is a vertical, is getting closer and closer to the height L. You can see that process. And it could be approaching L from below, from above, or just oscillating between L, but each time is getting closer to L. So these are the different manners that the limit can be approached. So it's read as f is a function defined on some interval. Okay. So here I like to explain to you what is some interval. Some interval meaning as long as you have one interval, okay, from a to infinity. So basically, take an example, right? You can say, well, this limit, right, depending on how close you want it to be, right? It could be from here. It could be here, from a to infinity, all the way to infinity, all the way that way, okay, horizontally. And if you have one, and you have many, you have as many as possible, because this interval works a to infinity, and you can have this one as this one can be a to infinity as well. So as long as you can identify one of it, usually it's reasonable, okay, reasonably large, and that's what it means. So when we see this symbol, the whole of the definition is is implied. The whole of the definition is implied. So please remember that. Please remember that. Okay. And the second definition that we are going to use is that what is horizontal asymptote, right? We have learned horizontal asymptote. Horizontal asymptote basically is, we've seen these horizontal asymptotes in the case of e to the power x, okay? So I'm going to show you a couple pictures. Okay, I'm going to show you a couple of pictures. Horizontal asymptote. Here we go. And we bring the, you see, in the case of e to the power x, right? In the case of e to the power x. Okay, so I'm going to graph e to the power x. E to the power x, okay? E to the power x, that's the curve. That's the curve, right? If I made some adjustment, I'm going to make some adjustments. So from here to say 10, okay? You can see this curve as x is approaching negative infinity, okay? As x approaching negative infinity, and the height, right? The function value is getting shorter and shorter as x is approaching negative infinity in this way, right? As x is getting negatively large, right? The function's value is from here, right? Even shorter. So it's getting closer and closer to 0. So in this case, we can say, okay, limit of e to the power x as x approaches negative infinity, e to the power x is 0. Is 0. Okay. And similarly, if you see e to the power negative x, right? So I drew this picture to show you. Okay, e to the power negative x. It's a picture that you also like to know. This function is, even though it's a tweak or is a, you know, it's a composition between two functions, including e to the power negative x, which is this picture over here, right? As x is approaching positive infinity. Okay, as x is approaching positive infinity. Oh, hold on, let me remove this arrow. Okay, I meant to use this arrow. So as x approaching positive infinity, the curve is getting lower and lower, meaning the function's value is getting slower and slower. In that case, we can say as e to the power negative x, the limit of e to the power negative x at infinity is 0, okay? So we've seen these examples, and these are the horizontal line. This is a horizontal line. And this horizontal line for both cases in the E, the horizontal line is called horizontal asymptote. So I'm going to draw this horizontal asymptote. These horizontal asymptote, okay, is a line that the curve will never touch, but it gets infinitely close to it. So this is a horizontal asymptote, and this other one has a horizontal asymptote as well. Okay. And so that's the definition of horizontal asymptote. We have learned horizontal asymptote before. So now we have a formal definition, intuitive definition. So for any horizontal asymptote is either, you know, the limit of the function at infinity is L, or the limit of function at negative infinity is L, right? So look at some other examples, such as 1 over x squared, right? We're going to come back to talk about these examples some more. We'll continue with our next useful property. This is a logarithm. I'm sorry, arctangent. Arctangent. This is a curve of arctangent. As you can see, arctangent is defined on the entire number line, but the range of arctangent, right, which is the horizontal span horizontally, right, is from negative infinity to positive infinity. The vertical span, however, okay, the vertical span is between negative pi over 2 to positive pi over 2. So this curve is larger than negative pi over 2 and smaller than pi over 2, right? That's a domain and range as we learn from trigonometry. And also, as you see, when x is approaching negative infinity, right? As x is approaching negative infinity, so let me use a different color. As x is approaching negative infinity, right, this way, the curve is approaching negative pi over 2 from larger than pi over 2. When x is approaching positive infinity, the blue curve is approaching positive pi over 2 from smaller than pi over 2. So this shows, you know, the way that we approach the limit. This is from above, this is from below, right? We've seen that picture in the definition of limit of function at infinity. All right, so the next useful property was the next thing we're going to learn, okay, is the next one, of course. Hold on, I'm going to clean this. Wait. There. This is a very useful property, and some of the pictures here is from the textbook, but let's look at the full version of it. The full version of it. Okay. Oh, too large. This one is if R is positive, right, and is a rational number, then limit of x approaching infinity is 1 over x to the power r is 0. And if r is positive and rational is a rational number, and x to the power r is defined for all of x, then when x is approaching negative infinity, the limit is also 0. What does that mean? What does that mean? I drew some pictures here. This is 1 over x. So when r equals to 1, okay, so this is the case when r equals to 1. R equals to 1, okay? Then this curve that we are pretty familiar with, right? When x approaching positive infinity is 0. When x approaching negative infinity is also 0. But in this piece is approaching from approaching 0 from above 0, right? This is approaching 0 from smaller than 0. And on this piece, right, I have a 1 over x squared. So we'll come back to this one. 1 over x squared. 1 over x squared is a situation, okay, is a situation that r is 2. Okay, 2 certainly is a rational number. And we can see as x is approaching negative infinity or positive infinity, the curve, they approach 0. They approach 0. And for this one, okay, which is 1 over x raised to the power 3, you can see these two are similar, right? And of course, in this case, r is 3. R is 3, right? It's similar. So these two Usually 1 over x to the power 3 doesn't show up as often as 1 over x because they have similar properties. The next one I wish to show you is that one is 1 over, square root of x. In this case, r is 1/2. R is 1/2. So in this case, you see as x is approaching infinity, positive infinity, right? This function is not defined at a negative number nor 0, right? The domain is x larger than 0. And in this case, you can see the function value is also approaching 0. It's also approaching 0. So I'm going to write it down, these limit for your for your reference. Okay, so you know the right way to express these limits, okay. Or x squared, 1 over x squared, right? The limit, right? These are the examples of the theorem, right? When r is equals to 2, right? When r equals to 2, then we have 1 over x to the power 2, right? 1 over x to the power 2. And then the limit, oops. Okay. And what do we say about the limit? The limit as x approaching positive infinity or negative infinity. Okay. Infinity, 1 over x squared. Okay, so I'm going to put it over here, is 0. Is 0. And if x is approaching negative infinity, it's the same thing. Okay, if approaches negative infinity, it also is 0. Okay. And the next one, the next picture we have here is 1 over x to the power 3, right? So another example one, r is okay, r is 3. So r is 3. When r is 3, the limit of it, right? So the limit as x approaching positive infinity, and of course it's going to be 0. But if x approaching negative infinity, it's also going to be approaching 0. But it is on this piece, on this end. Okay, this piece. Okay, hold on. So let me make some pointers for you to understand this. This expressing this corner, okay? And that is expressing this piece, okay? So if you like to find the relevance of this one is to express that limit approaching 0, and this piece is to express that limit approaching 0. All right, so I hope that's clear. Okay, so let's look at the other two. Okay, I added this to our study is 1 over square root of x. Okay, so it has only one piece. Wait, okay, 1 over square root of x. I think I have the picture ready here. Okay, I have the picture ready here. Right here. Right here. Okay, right here. So as x is approaching positive infinity, you have to take into the consideration of the domain, right? The domain, of course, is x larger than 0. So you take note of that. And so as x is approaching positive infinity and 1 over square root of x is approaching 0. So this is, we just explained the theorem. How do we express it mathematically, right? How do we express it mathematically? And here's how we express mathematically. Okay, so the limit, right? So we take this one. the limit as x approaching infinity at infinity is 1 over square root of x. Okay, and that is 0. For x, for 1 over, x root of 3, and I didn't put the picture there. It's just, it's a similar, but it's kind of similar to 1 over x raised to the power 3 in a way. They have the same domain, right? They have the same domain and range. Okay, same domain and range. So that was the explanation of this theorem, right? So why do we think that we have this theorem? It seems to be so trivial, and we look at some examples, seem to be so straightforward. Well, it's actually pretty useful. Okay, we're gonna use it in pretty soon. E to the power x, right? And the e to the power negative x, we just talk about it. And now about these properties, so these laws of limit at infinity. The law of limit at infinity, it is similar to limit of function at a. So individual limit must exist before we can add, subtract, multiply, and dividing, providing the denominator is not 0, and all of these properties will still apply. So that's about the law of limits for limits at infinity. So with that, in our new flashcards, right, we're going to look at some, applications of these new information, So how do we use them? So we're going to look at our homework. All right, we'll look at our homework. And for homework number 6, all right, so we're going to look at some questions to see how we can apply these properties, right? For example, how about this question, right? We want to evaluate this limit. I'm going to make it example number 1. Example number 1, we're going to evaluate this limit, which is limit. Wait, there. Okay. Limit as x approaching positive infinity. And we have 3x squared minus x minus 2 and the 5x squared plus 4x plus 1. Okay. I'm going to clear that arrow. So now when we see this limit, right, as x approaching infinity, and we actually cannot apply the law of limit. We cannot. Why? We cannot apply the law of limit because we have to check the individual limit exists. When x is approaching infinity, the top is approaching infinity, the bottom approaches infinity. So both limits do not exist. Okay. When something approaches infinity, then that limit does not exist. Okay. Now in this case, what do we do? Right? What do we do? So we're going to use that technique you might have seen before, is that we're going to transform this expression. Okay, so we can work the algebraic part. Algebraically. Okay, we can do the algebraically. It should be LLY. So we can work the algebraic part. For the algebraic part, remember we want to have limits, if possible, right? We want to have limits that looks like every individual piece has a limit. I'm making the funds a bit larger. So what can we do about that? Well, we can multiply by 1, right? We can multiply by 1. We use principle number 1, but this time I'm going to choose 1 over x squared. So why do we choose 1 over x squared? Well, remember, when we talk about limit as x approaching infinity, we'll be considering an interval from a to infinity. So we can choose that interval. So we can choose that interval to be that a to infinity to be a is so large, right? A is so large so that x will not be 0, right? And 1 over x squared is not 0 as a result. And then we can we're just basically dividing the top by x squared, the bottom by x squared by doing this. Okay, so multiply by 1. However, algebraically, you explain it really. Okay, so what do we have here, right? We copy and paste here. So what I'm going, oops. So what are we going to do here? I will give you a final version as how to show it. Okay, so this is divided by x squared. And that piece is going to be divided by x squared. And that piece is also divided by x squared. We do it all, we do it to all the terms from top to bottom. Okay, and that is basically applying principle number 1. Okay, anything times 1 stay the same. So this transformation is done in that from a to infinity, we make a large enough. Okay, so a is positive and large. And you say how large? Hey, you can choose I'm going to choose a 10,000. Okay, you can choose, hey, another person may say, hey, I would choose a to be 20,000. They all work. Okay, as long as you have an interval, you have some interval that this is. So I'm going to show you that definition, right here. That interval, some interval, a to infinity. We have that interval in our mind, so we think of a is, well, x is in that interval is very large. So all of these can be carried out, and then we just simplify. We're going to simplify this. An x squared reduce, so we have 3, right? And x over x squared, so we have x under 1 left. And 2 over x squared cannot be reduced. And over here, that's a 5. And this one, x, take away the x in the bottom, and 1 over x squared. And this way, the individual limit of 3, right? The individual limit of 1 over x, right? 1 over x, that limit is 0, right? We have learned that moments ago, right here, right? So we're applying this theorem. And the next limit would be the limit of 1 over x squared. So the limit of 1 over x squared, it is also 0, right? We have studied this theorem, so we're applying this theorem. And of course, the limit of as x approaching infinity at 5, well, for 5 is also 5. So now each individual limit exists. Okay, all the individual limit exists. And then we can apply the law of limits. And what is that law of limit? You can add, subtract, multiply, divide, provided the denominator is not zero. So the next step, okay, the next step about this given limit that we are to be evaluating is going to be, we're going to be evaluating this limit because the latter algebraic form is the same as the previous, right? These two are the same algebraically as x is large, right, in that interval. And now we can apply the limit, the law of limit. And how do we apply the law of limit? Law of limit is, here you have limit of sum is a sum of limits, right? The limit of sum, and limit of quotient is quotient of it. The limit of quotient is a quotient of limits, right? So we can apply all of these as a result. Okay, we have this form which demonstrated you have checked the theorem, you have applied property of limit law correctly. So limit, right? So this is 2 over x squared. So this step, right? I know that when you write it down, it feels like so tedious, right? But it demonstrates that you understand each individual limit exists, and thus you apply the law of limit. Okay, and over here you have a 4 plus 4, right? Limit of 1 over x. And the next one is limit of x squared, 1 over x squared. Okay, and then we know that the limit of 3 is 3 as x approaching infinity. The limit of 1 over x is 0 at infinity. The limit of 1 over x squared is 0 at infinity. So we apply the law of limit. So in the end, we are getting 3 minus 0 minus 0. The bottom is a 5 plus 0 plus 0. Of course, the final answer is a 3/5. In this process, you have demonstrated, the reader can see you have demonstrated that you understand how to apply the law of limit properly. Okay, so this will be, but how to show work? How to show work, right? How to show work. You can show work just like that. Okay, or you do this on the side, right? So one version you can show your work is that you do the algebraic part, right? If you have the tendency to forget about, forget to write limit, right? You can go from this step to this step. You can just do it algebraically. And right, this is a version 1. And the other way you can show work is that you just go straight to this. Okay, you can just do this directly. Okay, you can do vertically if you wish. And you can even skip this piece. You can skip this piece. Okay, so that's another version. So this is one version. And you can quote the theorem, right? You can quote the theorem to say that, this you're really using this theorem. But this theorem, because it's so obvious, I believe that most people who read the work, they know it, right? And pointing this out is helpful. It's helpful, right? Just reflected, you check the limit before you do. So pretty much that's how you show your work. Okay, that's pretty much how you show your work. The second version, okay, so work. As you get better, you can just do this part. Second version. Version number 2. Second version, you can just show this piece. Right? You don't even have to show this step. And that step can be, it's optional. And as you're getting better, then you can just go directly like this. If you insert a couple steps to show how you've done the fractions, that's fine too. Okay. The important part is if you start with limit, you keep that limit sign with you. If you start with algebra without the limit, and then you just keep working, and then you attach the limit. Okay. You don't start a limit and then you drop the limit, and then you have the limit coming back and still using those equal signs. That would be confusing, because you understand when we consider limit, right? When we consider limit, we do have a specific definition. We have a specific stage set, which is defined on some interval. And so this whole thing apply. The algebra part doesn't have this part apply to it. Okay, the next question I think I would like to do is this one, right? We have a function. We're looking for, I'm going to do part of it. This is one of the homework questions. I'm going to do the horizontal, we're going to find the horizontal asymptote, right? We have this function here. So this is example number 2. The function we have is the square root of 2 times x squared plus 1 divided by 3x minus 5. Okay. And we want to find the vertical part. I think you guys should be fine with it. But I will mention that at the end of this question. We want to know these limits. Okay, so we want to know these limits. The limits when x is approaching infinity, okay, of this piece. We want that. And we want the limit when x is approaching negative infinity. And we also want the limit as x approaching a fraction, which is 5/3. 3, 5. From larger. Okay, and the fourth limit we want to find out is this piece. From smaller than 5/3. Okay, so we're gonna basically, the first 2 is about horizontal asymptote, and the latter 2 is about vertical asymptote. Okay, so let's get started. So let's get started with this piece. Okay, the first one. To find this limit, the algebraic part is that, well, as x approaching infinity, right, there's an interval large enough. And so we can assume x is positively pretty large, and we can choose an interval, say, from a very large number to infinity. So this whole thing will be defined there. And the main issue here, as x approaching infinity, the top is going to be approaching infinity. The bottom is also going to approach infinity. So have an infinity divided by infinity situation. And in this case, we cannot use law of limit. And you can also, okay, so don't do this. Okay, and you claim that you have an infinity over infinity. Infinity divided by infinity does not equals to 1. It does not equals to, it does not equals to 1. It does not equals to 0. It does not equals to another infinity. Don't you do this ever. Okay, infinity divided by infinity, it's very uncertain. It's very uncertain. Okay, so don't do that. Okay, so don't do that. And then what can we do? Right, so don't do this. Let me put it here. What can we do? We're going to try to use the properties we learned here. Right, we're going to try to use these properties. To use that property, we can multiply by 1. Okay, if we want to handle the algebraic part, right? So we can handle this algebraic part, right? So I'm going to choose think out aloud. Okay, I'm working on something on the scratch paper. Okay, I'm doing all of these work is from a to infinity, right? Assume x is in that interval, right? I consider the setting of the limit. Wait, here, right? I consider setting from a to infinity, so x and a is large. A is large, and a is larger than 0, and it's very large. As large as you wish. Okay, just pick a number. It will work. Okay. So with this assumption, what you do is that you're going to do some transformation. Transformation, the goal of the transformation is to reach a certain point, we can identify some individual limits, and those individual limits exist, like in the previous example. And as a result, we can apply the law of limit. Okay. And in this case, of course, the principle we're using is going to be 1. Okay. And you can choose to multiply by 1 over x on top. And the bottom is going to be 1 over x on top. This is equivalent to say you are dividing every term on top and bottom by x. Okay, so this piece comes down, and this piece divided by x, and that piece is divided by x, and this whole piece is divided by x. Okay, this whole piece is divided by x. Simplify, the question is that what, on the top, right? If there's a square root, we're thinking, can we take this x inside? So that it's going to be transformed into, if we take the x inside, it's going to become x squared, right? It's going to become x squared. But we also need to be careful because we need to know the sign of x. Why? We know these facts. Okay, the square root of x squared is equals to the absolute value of x. And the absolute value of x is the same as a piecewise function. 2 pieces. If x is positive, or 0, the absolute value of x is the same as x. If x is negative, the absolute value of x is its opposite. In other words, right, if x is positive, right, we need x to be positive, so we can forget about 0, right? We just need x to be positive because x is in here. We just need x to be positive. If x is positive, the absolute value of x squared is going to be equals to x. If x is negative, then the absolute value of x squared is going to be its opposite. Okay, I hope you guys see that. And now in our current situation, okay, x is in this interval, so x is large, right? X is large. So when x is positive and large, x is the same as square root of x squared. So in this case here, right, I can safely take x, right, inside the root. Okay, inside the root. And become square root of x squared. Now it is inside. You see from here to there. Okay, we're going to use the latter part. We're going to use this part next. Okay, for the next limit, x approaching negative infinity. And now we can divide x squared into this piece, right? And we can also divide x squared into 1. So we just basically splitted it like that. Now, of course, we can simplify this. That's a 3. And that's 5 over x. That's a 3. That's 5 over x. Now we have 4 limits in our consideration, right? The limit as x approaching infinity on 3, the limit of f5 over x as x approaching infinity, the limit of that piece, and this is really 2. This is really 2. Okay, so I'm going to write down one more step. Okay, so this is just 2. Okay, so these limits, okay, these limits as of 3 equals to 3, right? And that limit of 5 over x, or 1 over x, or 5 over x, that's a 0, right? We're applying this piece there, right? We're using this theorem here. And 1 over x squared, 1 over x squared, that limit is also 0. And what else? When you take a limit, it's going to go across the root, the square root. And we have the composite function, right? Composite function, because root function is continuous. We can take a limit across the root. Okay, so this limit, right, this limit of this piece, okay, would be the same as when we take a limit, we bring the limit to the inside. You see that? So we apply that property of limit when we have a continuous function, we have a composite function, and the outside function is continuous. Okay, so this piece is going to go here. There. Okay, and what would that limit be? That limit will be written, right? That limit can be written in the following way. Okay, so if you want to write it very concisely, right? So this is the root of this limit. So you can apply the law of limits, right? So you can separate it into limit at infinity at 2, for 2, limit of 1 over x squared at infinity. And of course, that limit is square root of 2. You have checked each individual limit that they have exist, right? Look at all these scratch paper work, right? We're gonna have to organize it. So now by this time, we can take limit for this piece. And the limit for this piece, finally, is going to be equals to, right? We're gonna replace this piece by that. Right there, right? Remove that equals sign. And the next step is going to be taking limit on the top, right? Taking the limit on the top, which is on this piece. Taking the limit in the bottom. Taking the limit on 3. Taking the limit on 5 over x. We have checked each individual limit exists, and we have done this piece, and that's the square root of 2, right? So the bottom is 3, right? Because this piece is 0, right? 3 minus 0 if you want to attach it, just to show the reader. And the next step is that you can take the limit across inside, right? I mean, if you want to really follow, all those theorems to the T, right? And that equals to 3 in the bottom. And the top, you can write it down this way. And soon enough, you'll get into root 2 over 3. That's quite a process, isn't it? Okay. This shows you how we follow each one of these rules of limit, the laws of limit at infinity. So this piece is found. This piece is found. Okay. How do you show your work properly? How do you show your work properly? Right? If you show work, right? You can do the algebraic part separately, right? Pretty much you copy and paste all of these, right? Okay. You can show work, but certain part you can take them off. You can keep this. You can basically skip this step, really. Okay, just remove that. Keep it simple, right? But you do want to show this step though, from here to there. And you want to tell the reader, what have you done? If x is a positive, right? If x is a positive, and that's what you have. Okay, right? So from, wait, let me put it in the wrong place here. It's okay, either line is okay. And this step can be optional, right? That step can be optional. And then you get to the last one, right? So really just a 1, 2, 3, 3 steps. You can quote the theorem, right, about these limits, right? And then this step you don't have to show because you showed in ladder time. Okay, you showed in ladder time. So you can just show this piece. You don't have to show these. Okay. So then the latter part would be just like that. Okay. And that's it. That's how you can show your work. How you can show your work. If you separate the algebra part and the limit part. Okay, this has its advantage because you think you don't have to worry about, oh, I dropped the limit, right? So when we do it in a rush, we have tendency to do that. The next limit that we should talk to you about is this one. Okay, this is going to be interesting. But luckily, okay, so let's look at this limit. Luckily, we already have prepared, right? We have this piece. We have this piece. Because when we consider this limit, right, when we consider this limit, this is when x is approaching infinity. When x is approaching infinity, that interval of our work, that interval of our work will be changed. The interval of our work, right? It's no longer is a to positive infinity. It's going to be negative infinity to a. And a is going to be negatively large. Okay, a is negatively large. Okay, a is negatively large. You can think of a as negative 10,000, negative 20, right? Whatever number, but you have an interval which is negatively large enough. As a result, you know you can see x is negative. If x is negative, then the square root of x squared is negative x. That is also to say, if you bring the negative sign to the other side, you can see x is equals to negative of square root of x squared. Okay, so we're gonna use this piece. And the other algebraic part actually are rather similar, except that we're gonna have some change. Because here, right, at this step, okay, this I copy and paste the work we did before, right? Don't forget, x is negative. So x equals to negative of x squared, square root of x squared. So we bring that into the picture. Okay, because we're working in this interval. Now, when we replace x by, square root of x squared, we have a negative sign. So let me show you this way. Okay, let me show you this way. So we have an x here. We have an x here, right? And this x will be replaced by negative x squares. This x will be replaced by negative x squared. So we have a negative sign. This negative sign is going to be staying outside in the next step. And the square root of 2x squared plus 1 over square root of x squared, and they're going to be brought together. And then so everything is the same except you have a negative sign as extra. And you can bring the negative sign in the front of the entire thing. Okay, so that's a different part. And the rest of it are similar. The rest of it are similar. Okay. And we will have that limit, of course, approaching negative infinity. And over here, you have one x is approaching negative infinity here, negative infinity, negative infinity. They're also true, right? According to that law right here. Wait, this one, right? So for negative infinity, it's also true. So when we take x approaching negative infinity, so this will get to that piece will be replaced by this piece. There's a negative sign. Then that negative sign, you actually can bring it outside. Why can we bring it outside? Because the law of limit, right? You have a constant, multiply the function. When you take limit of a constant times function, this is -1 times the function. And all of these functions has limits, so you can bring the negative sign outside. Okay, you can bring the negative sign outside. So you're gonna have equal of a negative sign there. And the rest is the same, okay? The rest will be completely the same. So I'm going to copy and paste all of these, right? And of course, this equals to, I have to make some changes accordingly. This will be negative infinity, negative infinity, negative infinity, negative infinity, negative infinity, negative infinity. And there's a negative sign tagging along. Don't forget that. Okay. I should not be forgetting that. Otherwise, I'll be in trouble. I have to do it all over again. And for you, if you forget that, you could lose points. You could lose points. Okay, so I'm double check. So please, you too, double check our work. Okay, you can express them vertically, but here, I'm running out of space. If I do that, it will be so many lines. So this way, it may be easier for you to see it. So I can separate them into something like that, and not too vertically long. So this is the second limit. Okay, so we have, according to the definition of horizontal asymptote, right? We have two horizontal asymptotes. One is a negative root 2 over 3, when x is approaching negative infinity. And the other one is root 3 over 2, when x is approaching positive infinity. So we have two horizontal asymptotes. Okay, and these two horizontal asymptotes, so you can write it down, f, right, has two horizontal asymptotes, plural, and they are y equals to negative root 2 over 3, and the other one would be y equals to positive root 2 over 3. So let's look at a vertical asymptote, right? The other two limits. Vertical asymptote is something we have defined before, right? So I'm going to bring up the definition for vertical asymptote, which is back at the beginning when we introduce limits, right? Do we have it here? Right here, vertical asymptote, right? If any one of these is true, then we call that vertical asymptote, okay? X approaching a from larger, smaller. So here we just look at two limits. Now, when this limit in consideration, okay, so let's do one at a time. When this limit is in consideration, you can see, unlike approaching x is approaching infinity, this time we don't need to do any algebraic manipulation. Why? Because we have a situation when x is approaching, remember the definition of limit, when x is approaching 5 over 3 from larger than 5 over 3, right? 5 over 3 is a finite number. 5 over 3 is a finite number. So what you see is that, let me draw a line, okay? Let me draw a line so you can see what kind of situation is this. Okay, so we have number 5 over 3. That's 5 over 3. 5 over 3, so x is approaching 5 over 3 from larger than 5 over 3. And the 5 over 3 is actually not in the domain of this function. When x is approaching 5 over 3, the top function is a continuous function. You can plug in, right? But you cannot plug in for the whole thing because it's not in the domain, it's not continuous. So you cannot plug in the product, so don't plug in. So what do? You will imagine when x is approaching 5/3, 3x minus 5 is going to be approaching 0 from larger than 0. So let me write the narrative here. When x, right? When x is approaching 5/3 from larger, right? That means x is larger than 5/3. Okay, we're getting closer and closer, as close as possible. As a result, 3x minus 5 is approaching 0 from larger than 0. The denominator approaching 0 as close as possible to 0, but never 0, but the top. What does the top approach to? Right? As x approaching 5/3 from larger than 5/3, this is approaching a finite number, approaching a fixed number, a finite number. And you can figure out that finite number. How do you figure out that finite number? You can just plug in this number in the place, right? And you evaluate this. Okay, I just have to do it. Okay, so you're approaching a number. This number is fixed, it's a finite number. 5 squared over 9. So 2 times of 25, that's going to be 50. Right, it's almost not important as what the value of this number is. Really not important. So this is 50/9 plus 1. So this value is a finite number. The top approaching a finite number, the denominator approaching 0, but positive. So this entire thing is approaching what? It's approaching positive infinity. So by definition, as x is approaching a number from larger, right? So let me show you that piece right here. This definition, this is what happens here. Okay, therefore, right, by definition of vertical asymptote, you can say x equals to 5/3 is a vertical asymptote. Is a vertical asymptote. Okay, and over here 5/3. Sorry, I removed it. Okay, now approaching 5/3 from similar analysis. Okay, but this time x is approaching. So this piece has to be redone. Okay, approaching 5/3 from smaller. So x is less than 5/3. So this is approaching 0 from smaller than 0. Wait, sorry, from smaller than 0. A numerator is still approaching a finite number, right? In fact, the numerator is a positive. It's approaching a finite positive number. Positive, the numerator is always positive. Range of a root function, right? And therefore, this piece is approaching negative infinity. So by definition, this time, right? By definition, this time, this piece applies, right? This piece applies. And therefore, we can say x equals to x equals to 5/3, right? Is a vertical asymptote because both conditions are satisfied. in this definition, if any one of them is satisfied, now we have both satisfied, right? So this is a vertical asymptote. Both applies. Okay, both is true in this case. Okay, so when we approach 5/3 from smaller or larger, it's satisfied. All right. If you want to see a picture of this, even though we don't really need to draw the picture, you certainly can. You certainly can, right? You just graph this function. Graph this function so you can see better that's a curve. Okay, so hold on. I'm gonna make some adjustments. There. Make this wider this way. Okay. That function. Move up a little bit. Right, so the vertical asymptote is here. The horizontal asymptote, we know the horizontal asymptote, we have two of them, right? So let's take a look. Okay, since we have done all the work, and we're gonna draw the vertical asymptote and the horizontal asymptote. The vertical asymptote, let's draw the horizontal asymptote. We have a √2/3. Right, vertical, that's horizontal asymptote. We're gonna make it blue. Right, broken line, thin. We have another one, which is negative. And here we go, horizontal asymptote, right? And the vertical asymptote, 5/3, right? 5/3. Vertically, we want to use red, broken, boom. Wait. Wait a second. I did something wrong. Wait, 5/3. Did I choose too big a number? Dash. Cannot plot this expression. Oh, cannot plot that expression. Delete, see what happens. Okay, it used to work. Let me choose the view. Maybe this is -10, or maybe this -10, +10. I'm gonna turn on the light. Well, the view, so maybe -3, +3. See, this will look better. And the vertical asymptote, it used to work. Okay, 5/3. -10. 5/3. +10. Red, broken. That works. Okay, I probably typed something I'm not aware. Okay, so the vertical asymptote. So how do we express these equations of horizontal asymptote? You need to understand, right? Some of you, I'm sure you know, but I just want to clarify. This one, hold on, actually, this way of writing may not be that clear. Okay, so what I'm going to do is that I'm going to make a little table. okay, to express. So there's 4 columns, okay? And I'm going to say H S asymptote, right? Asymptote. Did I pronounce it correctly? SASYMOMTTOT. Yeah, that's correct. Horizontal asymptote, right? Horizontal asymptote, vertical asymptote. I'm going to change it to H to V. Okay. I want to mark them clearly for you, right? Even though we have just pointed out, you know, the vertical asymptote, that's the vertical asymptote. We have only one, just one vertical asymptote. So we don't need 3 columns, we don't need 4 columns, just 3. The horizontal asymptote is y equals to √2/3. That's 1. And the other one is the horizontal asymptote. This is negative. And the vertical asymptote is right here. We're gonna make some pointers so you can see who they are. Okay. So vertical asymptote, this is the red, right? The blue. And we have this piece goes here and that piece goes there. Okay, I hope that's clear. Okay, so if some of you need a review on line equations, right? These are vertical line, horizontal line, and how to express them. All right, I think this lesson has been long enough. It's been long enough. I think I'm gonna stop. Okay, thank you for watching.